Hello pre-calculus students and seekers of truth. In this video we will talk about horizontal asymptotes, vertical asymptotes, and how they are related to domain and range. So let us look at the semi-formal definition. There's a more rigorous definition that we will use later on in the course. We will explore horizontal asymptotes in much greater detail. But right now, we're going to learn just enough of the definition so that we can use and apply it to domain and range. So, if x approaches a finite number when x gets large, then and that finite number, let's call it k, then y equals k is a horizontal asymptote. So let's say you have some graph here, and as you type in, and this is probably the most common thing we see, that as you punch in really big number for x, f of x starts to level off. It starts to level off here at some value, whatever that is. It could be 5, 10, whatever. We'll say k is a placeholder right now. Right? So if you plug in really large numbers, then f of x, the y values, start to level off, then we can say that that is a horizontal asymptote. We can also say really large means that it could also be negative. Okay, this doesn't, so plus or minus infinity is what really large means. So if f of x gets very starts to level off as you put in large negative numbers, then wherever it levels off, that's a horizontal asymptote. For vertical asymptote, we're going to define it in a more algebraic way. If an input k causes the denominator to be 0 and the numerator to be non-zero, then, that's a typo, then the line x equals k is a vertical asymptote. So in my example here would be if, and we've seen, you've seen hopefully vertical asymptotes before. If you have a graph that looks something like this, like that line, and then there's like an imaginary line here, and the graph maybe does something like that, right? So this line here would be a vertical asymptote. And algebraically, we can identify the vertical asymptote as the place where the denominator is 0 and the numerator is non-zero. If they were both equal to 0, if the numerator and denominator are both 0, then f of k has a hole. Okay, so we'll talk about what a hole means in a minute. So let's just attack this problem here, and then we'll reference our previous definitions. So let's find the domain and range. And the first thing that I'm going to do is I'm going to just factor this. These are some quadratics. So I can factor the top. This is going to factor down into x plus 5 multiplied by x minus 4. In the denominator, I can take out a 2. So this will be 2 times x squared minus x minus 12. So this will split, and we can factor this. This is going to become, well, the numerator is still the same, right? X plus 5 and x minus 4. And the denominator is going to be 2. And this term right here, this expression right here, rather, we can factor that into x. I believe that would be x minus, or x plus 3 multiplied by x minus 4. Okay. Now, let's talk about the domain for a minute here. The domain is fairly simple. The domain is all real numbers except negative 3 and positive 4. If you put in negative 3, you'll cause division by 0. If you put in positive 4, you'll cause division by 0. So the domain, we can say, is all numbers between negative infinity and 3, and negative 3 rather, in union with all numbers between negative 3 and 4, and in union with all numbers from 4 onwards to positive infinity. So the domain there is done. The range is going to take a little bit more work for us to figure out. Let's look at some asymptotes. Let's look at what happens if we put in 4, right? So this is what I mean. Let's look at the vertical asymptote definition. At x equals -3, the denominator is 0, but the numerator is not 0. Right? At x equals -3, if we were to plug in -3 on the top here, we would get -3 plus 5, so that's 2. -3 minus 4, so that's -7. So that would be -14 in the numerator. And the point is, in the denominator, though, we would get 0, because -3 in here would be -3 plus 3, so that would be 0. So here, the denominator is equal to be 0, but the numerator is not equal to 0. So x equals -3, the line x equals -3, is a vertical asymptote. That is a vertical asymptote. Now, what about 4? What about f of 4? Well, if you put an f of 4, in the numerator you get 9 times 0, so that's going to be 0. In the denominator you get whatever you get here, and 4 minus 4 is 0. So in this case, both the numerator and the denominator are 0. So you're going to have a hole, right? So x equals 4 is where you're going to have a hole. There's a hole that's going to occur there. Okay? So we've answered the domain question. We've answered the vertical asymptote question. There's a hole that's going to occur at x equals 4. And what else? Well, we can also answer the horizontal asymptote. Remember that when you have a polynomial on the top and the polynomial on the bottom, we can just take a look at the leading terms, right? So this is a bit of a review here from Algebra 2, that if you want to find the horizontal asymptote of a rational function, you can just look at the leading terms at the top and the bottom. You have x squared over 2x squared. So in the long run, the function is going to approach 1/2. Okay, so y equals 1/2 is going to be your horizontal asymptote. And the range, well, we still haven't quite figured what that is yet. All right, now let me just kind of put this all together by showing you an actual graph of what this thing looks like. So here I have the function. It's been graphed, right? X squared plus x minus 20. You see here that let's look at the domain again. If I were to put in, we said from before that the domain could be anything except -3 and +4. So if I were to put in f of -3, it would be undefined, because that's where this vertical asymptote is occurring here. And if I were to put in f of 4, it would also be undefined. So that's pretty interesting, because if you look at this graph here, it looks like this is perfectly filled in, but actually at f equals 4, it's totally undefined. Okay? Now let's look at the horizontal asymptotes that we discussed earlier. We think that the horizontal asymptote is y equals 1/2, and that's true because, and let's look at the definition again. If f of x approaches a finite number, right, if f of x approaches a finite number of k, when x gets really large, then k is the horizontal asymptote. So in other words, let's put in some gigantic numbers. So if I put in f of 10, if I put an f of 1, I get 3/4. F of 10, I would get 5.5 whatever. And if I were to put in like a very, very large number, you can see that that number eventually gets really, really close to a positive 1/2. Even if I were to put in very large negative numbers, so f of -1, I would get 1, and if I put in very, very large number, you see that I would get some value that's very, very close to 1/2. So we can conclude that y equals 1/2 is going to be our horizontal asymptote.